Building your first AI agent prototype usually feels pretty straightforward. You grab an orchestration framework like LangGraph, set up some nodes, add a few edges for conditional routing, and you have a working graph. Then you try to take that graph to production and you hit a wall. Orchestration alone doesn't give you a semantic cache, so you end up paying the LLM to answer the exact same question twice. It doesn't give you a vector retrieval layer to ground the answers in your own data, or a bitemporal memory system that lasts longer than a single chat session. So teams end up taping together 5 or 6 separate systems, a vector database here and an external caching layer there. When those seams start to tear, engineering time gets drained on constant maintenance, and your API bell climbs from all those redundant calls nobody is catching. The engineering team behind ChorusGraph lived through this integration headache. Their solution was to stop gluing separate tools together by hand and build one native execution engine, where the memory, cache, and retrieval layers were built-in, swappable components from the start. When you force incompatible software layers to communicate, data drops and latency spikes. A unified runtime strips out the friction, making the system stable enough to handle real concurrent load. Curious, when the developers ran their first internal test of this new engine against a standard framework, the results exploded off the starting line. The headline numbers painted a picture of immediate, massive performance gains. The native runtime appeared to be dominating the baseline system across every metric. But instead of celebrating the summary, the developers dug into the raw task logs. They found a major bug in their testing setup. The baseline framework wasn't actually calling its tools at all. The entire comparison was worthless. Unverified benchmarks easily mask broken code. Trusting those early, spectacular numbers would have meant shipping a compromised system based entirely on an illusion. The team threw out those early results and intentionally rebuilt the baseline framework. They ensured it was genuinely competent and calling its tools before they ran any new comparisons. When the complex multi-agent retest finished, the native engine actually lost. It performed worse than the baseline framework. Tracing the execution path revealed a caching shortcut was overreaching. It skipped essential logic steps. Bypassing these middle nodes produced a fast but wrong answer. They rewrote the architecture so caching only triggers when mathematically safe. With the reasoning chain restored, accuracy returned. Stripping out logic cycles to boost speed leaves you with a fast system that produces errors. True efficiency means preserving the reasoning chain, even if it takes a split second longer. They kept scrutinizing the data and found another source of distortion. Between 2 runs with 0 code changes, performance fluctuated wildly because the LLM's sampling temperature, the setting controlling randomness, wasn't pinned down. That discovery created strict new operational rules. Every variable must be pinned, every claim verified against evidence, and summaries treated with suspicion. They also committed to publishing their exact, unvarnished results. If the engine tied the baseline or outright lost, that data went into the documentation right alongside the victories. Progress requires a complete rejection of curated marketing data. You can only improve a complex system when you force yourself to look at exactly what is failing. That rigorous approach led to the canonical benchmark, Run ID 20260704212111. Executed on Azure, this test used real Gemini API calls against a highly competent baseline, with identical prompts, identical tools, and perfectly pinned variables. This chart compares ChorusGraph to the baseline. Single-agent finance hit a perfect 100%. Single-agent healthcare tied at 72.5%. But multi-agent healthcare reveals the separation. ChorusGraph leaped to 87.5%. A 30-point improvement with 0 errors and fewer total LLM calls. When you put an AI system under the complex stress of multiple agents working together, tight integration wins. A built-in runtime handles the load efficiently, while pieced-together systems buckle. Synthetic benchmarks only prove so much. The next step was a real production migration, taking a company's live website chatbot with 15 nodes, conditional routing, and retry loops, and swapping the underlying engine to ChorusGraph. Real users generate unpredictable patterns, and live production traffic exposed a deep bug in the compatibility layer that sterile synthetic tests had entirely missed. Because the bug was exposed, the team caught it, the team diagnosed it, and wrote the fix. Once patched, the new engine seamlessly passed all 46 and the live agent's existing production tests. You don't have to take their word for any of this. The system includes a tier of 323 offline, deterministic tests that record and replay real responses. You can run the entire suite yourself to check the engineering quality, and it requires 0 API keys to execute. True accountability means giving you the tools to break the system and verify the claims on your own machine. AI performance is a verifiable reality, not a claim you have to trust blindly.